we have Zhihao Wang from Nanyang Technological University and the University of Groningen talking about the Frobenius map for stated SLN skein modules.
Thanks for the introduction, and thanks for the introduction, and thanks for the organizers. So I will talk about the Frobenius map for stated SLN skein modules. So there are 4 parts. So in the section 1, I will briefly introduce the definition for the stated SLN skein modules. Then I will talk about the classical limit, and just you set the quantum parameter to be 1. So section 3 is about the construction for the Frobenius map for stated SLN skein modules for the magnitude manifolds. In this section, we have some restrictions for the order of the root of unity. And section 4 is about the Frobenius map for stated skein algebras. But here, there's no restriction for the order of the root of unity. So I think a new concept is just the magnitude manifold. So a magnitude manifold is a pair, Mn. M is a smooth oriented manifold, and N is a one-dimensional submanifold living in the boundary, and it consists of oriented open intervals. And in my talk, I will always assume M is connected. So this definition is just for the stated for the in-webs. I think Todd already introduced this, so it just consists of oriented closed paths or oriented graphs and probably embedded in M. So here there's only one thing to. So it is just so if this is marking, this is the marking. This is the inside of the manifold. So at the endpoint of L, I mean it is oriented. So at this endpoint, we require the framing. So the framing is just the normal vectors, right? So the framing is the normal vectors. The direction can be any direction. But at the endpoint, we require the framing is given by the tangent vector of the marking. So at this point, the framing is it can only be this. So yeah, this is the only restriction for the framing. So and then the other definition, I think they are the same as Tor introduced. So the state for an in-web. So it is a map. It is a map from the endpoints of the in-web to all these integers. So for example, you can state this guy with 4, or this guy with 5 if n is more than or equal to 5. So if there's such a map, we call this in-web a stated in-web. And we work with so in this talk, we work over a commutative domain with an invertible element V, and this V is it works as a quantum parameter. Previous picture, okay. Previous one, yeah. Pardon? N. Yeah, it is. So you mean the vertices? Yeah, invariant vertex. Yeah, it just means you have, yeah. So this is n equal to 3, right? So for every vertex, it is invariant or it is one valent. So the one valent vertex is called the endpoint. Yeah. So then there are some constants to define the skein relations. So the stated SLN skein module of a magnitude manifold. So it is a quotient of an R module. So this R module is really generated by all the isotopic classes of the stated in-webs. And then there are some relations. Then we quotient the relations. So these are the relations Tor introduced, the same relations. Yeah. So then we're going to talk about the classical limit. So for the classical limit, I just use set v to be 1. And in this section, I will give, I mean, if v is 1, it is a commutative algebra. It is a commutative algebra. So in this section, I will give algebraic generators for this commutative algebra and also all the relations among these generators. So in this data scheme module, so you see in the defining relation, so the first relation is the crossing change relation. So you see this guy we call this positive crossing. And this one is called the negative crossing. So this relation is the crossing change relation. And here you have the height exchange relation. But I mean, as Tor introduced, this is the orientations, right? But they're both wide. So the defining relations only involve for the height exchange relation only involve they have the same orientation. But actually, I mean, we can prove this is a new height exchange relation. It is just they have different orientation. So, so from the height exchange relation and the crossing change relation, we can prove. So if v is 1, so it is easy to say this guy equal to this, and this guy equal to this. So this is G, I, G. The orientation, orientations are arbitrary. I mean, this one just means you can always cross, you can always pass it is transparent. And for this one, it just means you can change the height arbitrarily. Pardon? Free. You mean V? Or V is the quantum parameter. So in the so you say all these constants, they are defined. So this guy is V. So all these constants are defined by V. Yeah. So if V is 1, you say then this guy, for example, this guy will become -1 to the power of n-1. Right? So for example, if V is 1, you say that this will become 0. All right. So this is 1. This is 1. So this is why we have a relation like this. Right? And then the height exchange relation will become this. So then we can give a commutative algebra structure to the classical limit. So for any two stated in web, we define the product to be the disjoint union. And from these two relations, we can say this is a well-defined algebraic structure. And also it is commutative because it is the union. So it is commutative. So before I introduce the algebraic generators, I need some preparation. So here, this is the definition for fundamental groupoid. So X is a topological space, and all these EG are disjoint contractible subspecies of X. Then the fundamental groupoid is a groupoid. It is just a category, and all the morphisms are invertible. And for this category, the objects are just this EG, and the morphisms are the oriented paths between these objects. Of course, we consider the path up to relative homology. I mean, you can always move the endpoint. So if this is the path, you can smoothly move the endpoint. So yeah. So the morphisms are considered up to relative homology. And for a single group, we also regard this group as a groupoid. It consists of just one object, and all the group elements are the morphisms. So that's a convention. It just if the EG are empty, we just define this groupoid to be the fundamental group. So this is the definition for relative spin structure. Uh, so first, zeta is a unit bundle. I mean, it is just for every point, the fiber is the set of ordered orthonormal bases of the tangent space. I mean, here we assume M has a fixed Riemannian structure. So then for every P in M, the fiber is just is isomorphic to SO3. So its fundamental group is just Z2. There's only one non-trivial element in the fundamental group, right? Actually, I mean, the element is just you rotate, right? You rotate the vectors. So, and for any 2 points, P and Q, of course, OP and OQ, they're homotopic to each other. And we use O to denote this unique homotopy type. So then, then for any component E of A, so we want to lift E. We want to lift E to be a path in the boundary of UM. So we want to lift E to be here. So we say V is a path in the boundary of M. Maybe we say this side is the interior of M, and this is the outside. So if you want to lift a path to be here, so at every point, you just choose an ordered orthonormal basis, right? So for every point, you choose orthonormal basis, U, V, W. So we choose Ux to be the velocity vector, the tangent vector of this guy. And so this is Ux. So this guy is Ux. And we choose Wx to be the one that is orthogonal to the boundary. So, I mean, if this is the boundary and this side is the inside, we just choose Wx to be this guy. It is orthogonal to the boundary and also pointing to the interior of M. So then this will be Wx. So for the second vector, it is determined by the orientation of M. M is oriented, so this will be the Vx. So you can say that this process is smooth. I mean, if you move the point along E, all these vectors, it changes smoothly. So then you get a smooth path. Actually, this guy is also embedding. It is embedding to the boundary of this guy, right? So now we lift E to E tilde, and we define in tilde to be the union of this E tilde. E is, so this union comes over all the components of M, of A. So then we define the spin structure, the relative spin structure, to be a map from this relative homology group to Z2. And we require H maps O to be 1. O is this rotation. So in the following of this talk, we always assume there's a fixed relative spin structure. I mean, of course, if A is empty, I mean, this relative spin structure is just the Euro spin structure. Pardon? One dimension. In two, yeah, still one dimension. Yeah, 4 dimension. Yeah, now UM is 4 dimension. Yeah. Let me think. No. 5 dimension. Yeah, 5 dimension. Yeah. So in the meantime, we want to lift the frame to oriented arcs. So to do so, we first define something called the grid position. So if L is an A web, so L is an A web, and we say so E is a component. So this is E is a component of A, and this is L. For example, if the orientation is this guy, so we can isotope L to be in the grid position So when I say, so in good position, it just means the velocity vector at the endpoint is parallel to Vx. So Vx points like this. So then we just isotope L to be like this. Right. So it goes from this. So at every point we do so. I mean, if the orientation is like this, if the orientation is like this, then this will become this, right? So it will become this. So we can isotope L such that L is in good position with respect to every component E. So if so, we call L is in the good position with respect to the magnitude manifold. So then for any arc, for any framed oriented arc, it just means it is framed and also you have the orientation. So then for any framed oriented arc, so then this guy, we can lift this guy to this group point, to a morphism in this group point. So how we do so? So actually you see alpha itself, it already has two vectors, framing and the velocity vector. So, I mean, actually it is just an element in here, but we have to be precise. I mean, which one is the first and which one is the second and which one is the third. So, I mean, for example, maybe this is just part of alpha. Alpha is an arc, so there's no sink or source. So for alpha, we choose the framing to be the first vector and the velocity vector to be the second vector. The third vector is determined by the orientation of M. So if we do so, you say the endpoint of alpha tilde. So the first vector is the framing. So it is this guy. The second vector is the velocity vector. So it is Ux. So you say it is just so the endpoint of this. So the endpoint of this just lives in E tilde, right? So the first one is going up. The second pointing to this direction. The third one is determined by the orientation of M. So which just means this guy is a morphism in here. So for a framed oriented arc alpha, we just introduce a convention. So and IG are two states. So we use this guy to denote a stated arc. It just says so. Actually, just you state the starting point. You state the starting point with with G. You stated the starting point with G, and the ending point with I. So this is just a convention. So the state for 0 is this. The state for the ending point is I. This is just a convention. So then we're trying to define the algebraic generators. So for any morphism in this fundamental group point and two integers between 1 and m, so this data, all this data uniquely determine an element in the classical limit. So first we isotope. So first we choose a good representative alpha, such that alpha is a properly embedded arc. It just means there's no intersection of alpha. So alpha does not intersect itself, and also the boundary of alpha lives in the M. And then we give a framing to alpha. We use alpha hat to denote this framed guy. And we have one requirement, that is the relative spin structure acts on this as 0. This is the only requirement. So, and then alpha hat is a framed oriented arc, because we also have the two integers. So then this guy will be an element in the stated skein module, right? So if we choose a different good representative alpha prime, so we still get the same element. So why? I mean, because of this guy. I mean, so this guarantees the difference between the number of the kinks is even. So if V is 1, this guy equals to minus A minus 1, this. So if V is 1, you have this relation. Of course, if A is odd, then the framing does not matter. But if A is even, the framing matters. And this guy controls the number of the kinks. So this condition guarantees, although we choose different good representative, I mean, we have the unique element. So, and then we will use this to denote the unique element. And then we define a matrix, an n by n matrix in this commutative algebra. The entries are defined like this. So here A is a matrix, n by n matrix. So now we are ready to give the algebraic generators. So, so I only work with the stated version, because for the non-stated version, I mean, Sakura already proved, Sakura already had some conclusions. I mean, it is just the classical limit. So if n is empty, the classical limit is the regular function ring of the capital variety, right? So if n is not empty, and we suppose all the components of n consist of this, so these are all the components. And if k is more than or equal to 2, and for each t between 1 and k minus 1, we use alpha t. Alpha t is an oriented path connecting E0 and ET. So I mean, the starting point is in E0, the ending point is in ET. This O is the identity metric, the identity element in this fundamental group point. Actually, this is just the fundamental group. Or then the commutative algebra is generated by all these elements and subject to the following relations. So if k is 1, then this is empty. If k is 1, you can say, I mean, this is the relation. The determinant is 1, and this is the relation, right? I mean, this is just the universal representation algebra, right? If k is 1. And if you add one more marking, actually just introduce one copy of the OSLN. OSLN is just the regular function ring for the SLNC. So then now, I think now we are ready to build the Frobenius map for stated SLN scheme modules. So the Frobenius map was already built for SL2 and SL3. For SL2, Zhihao and I think Tong Li and Tong Li and Furman, they built the Frobenius map for SL2, and Higgins built the Frobenius map for SL3. But for SL3, I think Higgins method only works for the surface, not for the general manifold. So, and to build the map, so the Frobenius map only exists when the quantum parameter is a root of unity. So we suppose, so V is a primitive mth root of unity, and also M and twin, they are co-prime to each other. So we assume the marking set is not empty. If it is empty, everything will become very, very complicated. So now we're trying to establish an linear map from the classical limit to this place, to here. So it seems like we can define this map on the algebraic generators and then check all the relations, but we cannot do so because there's no algebraic structure, right? But we can define this map, but we can consider this algebra. So we use this guy to denote the set of all the linear maps from this guy to itself. Then, I mean, obviously there's an algebraic structure for this guy, although it is not commutative. So then we can define an algebraic homomorphism from the classical limit to this algebra by defining this map on the algebraic generators and then check all the relations. So if we have this map F tilde, then we can define F alpha to be this. You say F tilde alpha is a map from this guy to itself. Then it definitely maps the empty skein an element in here, right? So, and also it is obviously this will be a linear map. F is the Frobenius map. I guess because people already built this map for the bygone, for the quantum group. I think they call this Frobenius map. Actually, for SL2, people call this Frobenius-Chebyshev map, Chebyshev-Frobenius map, because for SL2, they use the Chebyshev polynomial. Yeah. I think for the quantum group, they call this Frobenius map. Yeah. I mean, so just like Tao introduced, I mean, this is related to OQSLN. Yeah. So to check the relations, we first prove some relations in here. So I will explain what this means. So first, we look at this guy. So this M, it denotes M parallel copies of this line. So if this M parallel copy, it is this. You just take M parallel copy. I mean, of course, we'll take the M parallel copy at the end point. You should be careful with the height. I mean, you take M parallel copy in the framing direction. I mean, anyway, you can imagine this M parallel copy like this. So, but we have some restriction. So this one denotes M parallel copies of, so this is a part of M parallel copies of a stated arc. So it is an arc. So it is not a part of knot. So it is not a part of closed knot, or it is not a part of sinks or whatever. So this end connects to N. This end also connects to N. So this is our requirement. So if so, we have this relation and also this relation. And this is true. So there's no restriction for V. So this is true for all V. So this is the cross-chain exchange relation. So this is the height exchange relation. So the same. This is part of M parallel copy. So this is part of M parallel copies of the state arcs. And for this picture, so the orientations are the same. For this picture, they have different orientations. So these are the relations. So from all these relations, you can say if V is a root of unity and M, so V is a root of unity of odd M, and M and 2 in their prime. So if so, you say Q square will be a root of unity of M order. So this will become 0, and this will become 1. So this will become 1. So this will be 0. So you say we will have this picture and this picture. Right. So then, so this is some definition. So alpha is a stated framed oriented arc. It just means it is an arc, and there's framing and also there's states. So we use this notation to denote. We take M parallel copies of this arc or not. I mean, in the framing direction. So suppose L is a stated in web, and L consists of arcs. So it consists of arcs. So we define L to the power of M to be this. So you just take M parallel copy for each component. So if so, we suppose T1 and T2, that two isotopic stated in webs. There's no restriction for T1 and T2, such that there's no intersection between L and Ti. And then we have this equation. Right. Why this is true? It is just because this, right? You can isotope T1 and T2. You can pass through L to the power of N. So we have this lemma. Because of this lemma, we can define some linear maps, still the same L. Then we can define a linear map FL from here to here. And so for any stated in web alpha, we isotope alpha such that there's no intersection between alpha and L. And then we define So FL maps alpha to this guy. So from this lemma, we can say, so I mean, no matter how you isotope this alpha, this guy is well defined, right? So it does not depend on how you isotope alpha. And also, if alpha and beta, if they are isotopic, still it defines the same element, still because of this lemma. So what about the skein relations? Because the skein relations are local relations, so obviously FL preserves the skein relations. And M is the order. Little m is the order of the root of unity. Yeah. So little m. Yeah. So then for any two stated in webs, so here alpha and beta, they both consist of stated framed arcs. So from the definition, we can say, so the multiplication of this will be the union, right? And this is trivial. This is the disjoint union. So then we define this guy to be a subvector, space of this algebra, linearly spanned by all such FL. So from this relation, we can say this guy is a commutative algebra, is a commutative subalgebra of this algebra. Right? So the product is preserved, and also this guy equals to this. So actually, we will define the F tilde. I mean, this will be the codomain for F tilde. So to define such F tilde, we should find the images for the generators. So now, yeah, sure. It is a commutative. From the above discussion, we know this guy is a commutative subalgebra of this. This guy will be the codomain of the F tilde. Yeah. So I would define F tilde from the classical limit to this guy. Yeah. So now I'm going to introduce the potential images for the algebraic generators. So alpha is a morphism for the fundamental group point, and you have two integers. So basically it's kind of the same process. We choose a good representative alpha such that alpha is properly embedded in M, and we give a framing to alpha. And we require H maps the lifting to be 0. So then we obtain an element here. Still, I mean, so if we choose a good representative, still they're the same. Basically, the kind of the same reason, then they're the same. So this uniquely determine. So all this data uniquely determine an element in the commutative algebra. So we use this guy to denote an n by n matrix in this commutative algebra. The entries are just this guy, just this. So this is just this. So now we have the potential images. So to define F tilde, we should also have to check the relations. So now we have some relations for the images. For any two morphisms in the fundamental group point, if the product makes sense, then we have this. For any morphism eta, we have the determinant is 1. And for any identity element, A times this matrix is the identity matrix. So this is just to recall the, so here we just recall the algebraic generators for the classical limit and the relations. So these are the algebraic generators, and these are the relations. This, right? One more. Sij, this. This one is this. It's just this guy. This guy. F alpha ij. So alpha I. So this guy is an element. So this guy is a framed stated arc. So first you have an arc, and then you give a framing. So it becomes alpha hat. Then you give two states. So this G, yeah, that's stage. So G is the state for alpha for the starting point. Yeah. So we have this relation. So if you compare the relations for the algebraic generators and the relations we calculate, you say here the determinant is 1, here the determinant is 1. Right? So here it is A times the identity is the A times SO is the identity. So here A times O is the identity. And here you have this multiplication. Still you have this multiplication. Pardon? Oh, capital A is a matrix. Where is the definition for capital A? This is capital A. It is an M by A matrix. The entries for capital A comes from this. It comes from this. So to compare these relations and the lemma, we can say this guy is well defined. So it is a well defined commutative algebra. It is a well defined algebra homomorphism, since this to this. But the definition of F tilde depends on the choice of the generators. Actually, we can prove. I mean, it is independent of the choice of the generators. So for any L consisting of stated framed origin arcs, so we can prove F tilde maps L to FL. So I mean, this is unique. FL is unique. So which means, so F tilde maps every L to a unique element, and the status. So the classical limit. So the status scheme module is linearly spanned by all such L. Right? You can always use, because you have boundary, you can always kill the sinks and the sources, and also you can kill the nodes. Right? So it is generated by all such L, linearly generated. So which means F tilde is unique. So it is independent of the choice of the algebraic generators. And also obviously, this guy is surjective. From the definition of this guy, this F tilde is surjective. So actually, this theorem actually implies the stated scheme module has a classical limit module structure. Right? So it is a map from here to here. This guy is a subalgebra of the linear maps. So it is actually, this is just an action. And if M is compact and N has finite components, this module structure is a finite module structure. This is very important. Why it is important is because if MA is the thickening of the PB surface, this lemma implies the stated scheme module is finitely generated over the image of the Frobenius map. Then it is finitely generated over the center. Then it means it is a fine. So it is a fine almost as my algebra. Then the unicity applies to the stated SLN scheme algebra. So so actually it is true for if M is compact and N has finite components. So now we are ready to build the Frobenius map. So there exists a unique linear map. So such that F maps L to this. So you say our definition for FL is F tilde L map this guy. And the definition for this is L to the power of M uni the empty. So this is just L to the power of M. Right? So now we have the Frobenius map. And we can also prove. So already introduced the definition for the stability map. This is the stability map. So if you have a disk, properly embedded disk, and also there's an open interval. I mean, this is just the three-manifold version for the stability map. So if you have this data, you have a stability map from this to this M prime and A prime. I mean, you get this by cutting MA along this disk. I mean, basically, the picture will look like this. Yeah. So this is the original proper embedded disk. And this is the oriented open interval. I mean, so this picture looks like the picture. Yeah. This picture looks like the picture Tao showed us, right? So then, the stability map commutes with the Frobenius map. This is also very important because this commutativity helps us to calculate some relations easily. I mean, for example, so this relation. I mean, if you take M parallel B here and also M parallel copy here, I mean, from this commutative diagram, so you can easily prove some relations. I mean, actually, it is not trivial. So, yeah, I mean, it is just this. So, if you first cut this, so it is actually here this commutative diagram can give us something like this. So this guy will equal to you have some Ci and this is M and M, but this have the same state. I mean, so from the defining relation, we will kill all these M parallel copies. So this data here could be different, right? If you kill M parallel copy using the boundary relation, so it will become this. I mean, so this I1, this is I1, so this should be I1 bar, I2, I3. I mean, so these three are different. This should be different. But here, I claim that actually they are the same, because for the different terms, they cancel each other. Yeah, this is just MA is the thickening of the PB surface. That Tao introduced the definition for the PB surface. So if MA is the PB surface, it's the thickening of the PB surface. It just means the PB surface times the interval. So if MA is the thickening of the PB surface, then the skein module has an algebra structure. So we will use this to denote the stated skein algebra. So if this is the case, and we assume sigma is connected, the boundary is not empty. If this is the case, then the Frobenius map is an injective algebra homomorphism. Also, the image lives in the center. So like I said, we can prove this guy is finally generated over the image of the Frobenius map. Then, which just means this guy is an affine, almost a Riemann algebra. So then, I will talk about the Frobenius map for state SL skein algebras for all roots of unity. So these are just some coefficients to define the OQSLN. So these are some coefficients. So the algebra is generated by this UIG. So both I and G, there are two integers between 1 and n. So these are the relations. And then, besides this relation, you also set the quantum determinant. So this is the definition for the quantum determinant. You set the quantum determinant to be 1. So then this is the definition for OQSLN. So, also mention this. So for the bigon is a surface obtained from the two-dimensional disk. So for the bigon, it has a Hopf algebra structure, and also the bigon is isomorphic to the OQSLN. And now we introduce the the concept called saturated system. So a saturated system is a collection of properly embedded arcs. So such that they are disjoint from each other. And also if you cut the surface along these arcs, the resulting surface only contains one ideal point. Now, for example, if this is the surface, maybe we introduce one inner puncture, then the saturated system will be this guy. This is the saturated system. So if without this puncture, it is just this. So then this UBI is the regular open neighborhood. It is small regular open neighborhood. So this will be UI. And also that disjoint is from each other. So for a saturated system B, we take a UB to be the disjoint union of this UBI. Lee and Sakura proved, so for a saturated system, I mean, UB is a subsurface of the sigma. So this embedding induces a linear map. So this embedding induces a linear map from here to here. And they proved this linear map is a linear isomorphism. This is true for general V. So now we assume the order of Q square is M, but now there's no restriction for M. And we set U to be this guy. And eta is just here, the rule of eta is the rule of Q. Eta is U to the power of 2n. So people already built the Frobenius map for OQSLN. So there exists an algebraic embedding defined by it sends every UIG to UIG to the power of M. So I mean, from the isomorphism of the bigon under the OQSLN, we can easily build the Frobenius map for the bigon. And also you can see, I mean, this is also easy to prove. So it maps every arc to the arc to the M parallel copies. So now we're ready to define the Frobenius map for the general surface. So sigma is essentially border the PB surface. It just means it is connected and the boundary is not empty. I mean, so this embedding induces two linear isomorphisms. So it is Lee and Sugura proved this, right? This is linear isomorphism. This is also linear isomorphism. So look at this diagram, isomorphism. So this UB is the disjoint union of the bigons, right? UBI is the bigon. If you look at the picture, I mean, because this is open, this is dashed line. Actually, this UBI it is just this. Maybe you can close this, but you leave a picture here. So this UBI is just the bigon. So then UB is the disjoint union of the bigon. So then the stated skein algebra is the tensor product of the bigon. So then we have the Frobenius map for the bigon. So you have the tensor product of the Frobenius map for the bigon. Isomorphism, you have a map here. It is embedding. Then you have an injective embedding here. An injective linear map here. So it is obvious, it is linear. But it is not obvious, it is algebraic homomorphism. So Ami hierarchy proved this. So if sigma is essentially border the PB surface and B is a saturated system, then for any stated in web diagrams, so L just consists of arcs. We can prove FB maps L to the power of M. So which means FB is independent of the choice of B. Right? So we just omit the substitute for FB. So we can also prove F is actually an algebraic homomorphism, preserves the algebraic structure. And also F commutes with the splitting map. So now we only built the Frobenius map for the for surface without puncture, with non-empty punctures. So here is a rough idea to build the Frobenius map for surface without boundary. So still sigma is a PB surface, and P is an ideal point. CP is a trivial arc. So this is an ideal point. This is CP. Then you cut CP. Then you cut sigma along CP. So you will get a. So this is the surface. If you cut this will become the hole. So this is the hole. And we denote this cutting surface as sigma p. So then there's a map, theta p, from the skein algebra here to the skein algebra here. Basically, the definition for this guy is, so for any stated in-web living in the surface, we isotope this in-web such that there's no intersection between this in-web and this disk or the monogon. So then we just define alpha to be alpha. So then the alpha will become an in-web in sigma p. So this is the definition for sigma p. So Lee and Segura proved this is a well-defined algebraic homomorphism. And for any if you choose two different ideal points, the kernel, they're the same. Actually, they conjecture this kernel should be 0. If actually theta p is injective if and only if the stability map is injective. So still the same thing. Now we cosine the kernel. Here we cosine the kernel. Sigma p has boundary, so that's the Frobenius map. So we try to restrict the Frobenius map to here, right? But I mean, to do so, I think there's some things to prove. Yeah. If the kernel is 0, then this guy actually will be the Frobenius map. And the people believe this kernel is 0. So from the restriction for the root of unity, we can say u to the power of 4n is 1. So especially, so I proved if u to the power of 2n is 1. So u to the power of 2n is 1 or minus 1, right? If it is 1, then this theta p is injective. So if u to the power of 2n is 1, then we have the Frobenius map like this. But to build this map, you have to prove the restriction. If you restrict this guy, the image lives here. To prove this, I think there's still some works to be done. I think I still have some time, so I will talk something about the central elements. So E is a component. So E is a component of the marking N. I'm sorry. E is a component. So now we're still working with the PB surface sigma. It is essentially PB surface. So E is a component of the boundary. E is a component of the boundary. So for every sigma and for every alpha, we denote alpha is the diagram. We denote E alpha to be the endpoint. So this is the set of endpoints of alpha on E. Or if you can see endpoints, or you can see the half edge, maybe half edge, something like this, half edge. So we define, then we introduce some map. So this is some definition. So A is a map. So A maps this guy. So this is the marking. So this is the marking. This is the half edge of the A map. A maps this guy to be 1. A maps this guy to be -1. But basically, if the half edge pointing towards the marking, we map this guy to be 1. If the half edge pointing out of the marking, it maps this guy to be -1. And so E is a component. E is a boundary component. Alpha is stated is the diagram. So we define this guy to be this. It is just for every half edge incident to this component. We sum over all this. So there's another definition. So I is a state. So still E is the boundary component. So we define something like K E I alpha. Alpha is also the diagram. We define this guy to be the cardinality of this guy. So C is the half edge. So such that AC acts on, I will explain this. So this guy is the state. So this is the state, S is the state. So you say S is the state. Is I. So I will explain this. So this is the action. So we define one X on I is the state, any state. And one X on I to be I minus 1 X on I. So this is the bracket to be M plus 1 minus I. So this is the definition for this action. So we define this actually just counts the number, some numbers of the endpoint of the half edges. So this half edge satisfies this. So it just basically just means if this half edge pointing into this guy, the state is I. If it pointing out of I, the state is I bar. I bar is this guy. It counts the number of half edges. It is this or it is of this form. So then, for any two such web, for any two diagram, we define this guy to be, this is E, still boundary component. So I, so it's sum over I, so sum over the state. That is K E I alpha K E I beta. So this is the definition for this. So then we have the following formula. So now I will also define some operation. So this is the boundary of the surface, and so all the diagram is negatively ordered. So then this we define an operation, and it's P just means the positive. So it just you push the endpoint in the positive direction of the boundary to the ideal point. So this guy will map this to this. I mean, of course, it is oriented. So this is the operation of P. So then we have the Frobenius map X. Alpha consists of X. Alpha consists of X. Consists of slitted X. So then this guy maps this equal to Q minus N M sum over 2 W P. So I will explain this. Plus E also times e to the power q to the power m, q to the power m times sum over e. Actually, this is a generalization for this formula. You formulated this formula for the SL2 case. So this is just you sum of all the crossings, but it is the sign crossing. This is the negative crossing, and this is the positive crossing. Yeah. Anyway, from this formula, we give some. We listed some central elements, and yeah, maybe I give one example. So maybe this is the boundary, and this is the inside of the surface. This is the inside of the surface. Then a central element will look like this. So this will be I1, I1, I2, I2, I3, I3, I4, I4. I'm going to use F to map this guy, and this guy is central. So actually, we believe that the whole center should be the stated in arcs. The stated in arcs, I mean alpha can say so the stated in arcs such that this guy is D. I'm sorry. Yeah, I mean, so if we introduce the order of this guy, so suppose the order of this guy is m prime, and the biggest common divisor between 2 and m prime is D. So then, actually, we so for this beta, if this is D, and this such that this is even, then definitely it lives in the center, right? The image lives in the center, and we believe so. This all the central elements. So it is of something like this, or it is obtained from the bed arcs. Maybe you need some localization. Yeah, maybe it is the elements like this, looks like this. So F tilde, so F alpha, the bed arcs. I mean, you use bed arcs to get some central elements. So the center should be formulated by these two. This kind of two elements. Maybe you need some localization. Yeah, I think that's all for my talk.